Okay. Okay, thank you very much, Sergey. Thank you very much for inviting me. I'm really thrilled to be here to walk through the historical room. It really is inspiring, especially due to the fact that although maybe I did not know many people in person, but definitely I read all scientific works and appreciate this scientific impact they did on the science we are actively involved in. Okay, so thank you again, Sergey. I lost, here. Okay, for the invitation, and again, I'm really enjoying staying here. Okay, so so the first talk I will be giving, I will briefly, or maybe not briefly, introduce a long-wave theory of thin liquid films. I'm almost sure that, for many of you, this will be sort of a trivial, but I'm sorry about that, but actually the main thing here is to educate students and not professors. Okay, so maybe some of you ask a question, where the hell is Israel? So let me just show on the map. Okay, so this is the map for Eurasia, and I believe that I don't need to introduce you this country, okay? But if you ask where is Israel, you see this is the place where there is no place to put even the name of the country on, so it looks like it's submerged in the Mediterranean Sea. But there is a little line here which shows a piece of land which is called Israel. Okay, so going back to science. Okay, so there are a few review articles. One of them is mine with collaborators, Steve Davis and George Bankoff of blessed memory. He passed away last year. Yeah, a year and a half ago. Which we wrote in 1997, and there is another review article which is in the same journal, Reviews of Modern Physics, and it appeared some 12 years later. So I remember I spoke with Omar Matar before he wrote the paper, and he said, okay, so we'll build our review article, will refer to everything which was before you wrote the paper, and so we'll concentrate on what was after that. Anyway, these two papers, I think, would be a nice introduction for students. What I'm talking about, at least today. Tomorrow and the day after tomorrow, I will talk about something else, but definitely related to this. Okay, so just a few basics. Well, okay, first, okay, we are in the modern times, so we need to explain to students why we are motivated of doing this and doing that. Liquid films, actually, they are very ubiquitous in many technological processes. One of them is liquid coating of solid surfaces to protect them or to do something else. And for example, one of the applications is a cooling of surfaces by running liquid film, like you have a nuclear reactor a column standing in somewhere, and you want to cool it down because otherwise there will be another nuclear catastrophe. So you want to cool it with running film or running liquid, and so this is another application. There are many biological applications like human airways, lungs, bronchi, and all of this business. So it turns out that there is a very well-known disease among babies. So the airways, because the airways are actually coated with a liquid layer from inside. And then it turns out that sometimes the liquid layer coating the inner side of the airways gets bigger, or there is accumulation of liquid, and then it blocks the passage of the air through the airways, and this is a very well-known disease. So definitely some answers need to be given how to avoid problems. And it tear films in the eyes. that many people suffer from. It's called a dry eye syndrome. Okay, so there is no mucus layer on the eye under the lid, and then you feel burning effect on your eyes when you look, especially in the sun. So in all of these, liquid films are involved, and of course many natural phenomena. Some of them are gravity currents. You see water running, or lava flows. Okay, it can be also modeled with this approach. Okay, so I hope I convince you it's very important topic, at least to listen to. Okay, so let me begin with a problem which apparently is unrelated, but it has some relation to what I will be speaking about. Okay, so the problem goes back to Reynolds, late 19th century, and it goes like this. Imagine we have a liquid surface, a solid surface, which is given here, and there is a solid planar surface underneath. And okay, so what happens is the following: we have a liquid here, everywhere here. Okay, and this solid surface is moving with a given prescribed velocity. It can be uniform, it can be constant in time, it can be varying in time. But basically, for the sake of simplicity, let's talk about uniform velocity of the surface. Okay, so what we understand is the following. Okay, we have a liquid here, we have a liquid here. If this guy is moving, in this case, to the right, so it drags liquid after it, okay, by viscosity. Okay, so the liquid wants to go through this channel, and the channel is between, is sort of sandwiched between this moving surface and the static surface above. Now let's assume that the location of this surface, or the shape, is given in some reference which is spanned. Okay, x is the horizontal direction and z is a vertical one, normal to it. And let's assume that the equation, the location of this surface is given by a function h of x. Z is a function of h of x. Now let's also and let's assume that the pressure in the liquid is the same here, and it's given by some PA. Okay, now an additional assumption. Let's assume that the liquid is incompressible Newtonian liquid, so it makes it easier to handle mathematically. And let's also assume that the maximal value of the gradient of the surface, of this upper surface, is given by alpha, and it's much smaller than 1, which means that the inclination of the gradient of the curve, it doesn't have to be, by the way, a line, a linear function. It may be whatever you want, but the main assumption is this. So the gradients are very, very gentle. Okay, so given this, and this is called slipper bearing. Okay, so given these assumptions, so we want to treat the problem mathematically as simple as we can. And under the assumption given here, especially under the assumption that the gradients are very small, so we can assume that the flow here in this channel is sort of one-dimensional in the x direction, in this direction. Okay, okay. So now, okay, let's write the equations. So the equations from the Navier-Stokes equations will get. Okay, sorry. This is a continuity equation, a mass conservation equation in two coordinates, a two-dimensional system. And okay, so this is what is left after we throw away everything we don't need in the z direction, in this direction. And this is the reminiscent of the Navier-Stokes equation in the x direction. Okay, so what we get here? We get the mass conservation equation. We have this pressure a gradient in the z direction, just left out of everything, and we have this simple linear equation which is left from the Navier-Stokes x component. Now, how about boundary conditions? By the way, mu is the dynamic viscosity of the liquid, and V, it's with the two components U in the x direction and W in this direction. P is pressure. Okay. So now how about boundary conditions? Boundary conditions are very simple. Okay, the pressure we send will keep the pressure the same here and here. And this domain will be between 0 and L. Okay, so we have the pressure here at this location and at this location are the same, PA. For the longitudinal component of the velocity, we have U at 0. The variable for U, it's actually Z. Okay, so it should be U at Z equals 0, equal to U0. This is the imposed velocity by the lower surface. U at H is 0. Okay, at this location, the component of the velocity in the longitudinal direction, in the x direction, is 0 because there is no penetration, and there is no slip, no penetration. And for W, we don't need two boundary conditions. We have only a first derivative, so we want just one boundary condition. W at 0 here, it should be 0 because it doesn't flow through the liquid, the surface. Okay, so just to summarize, these are the equations and the boundary conditions I showed in the previous slide. Okay, so now we want to solve the set of equations and the boundary conditions. So what do we have? Okay, so we have from this equation, we have P, and I forgot to mention that we don't have time dependence, so everything is steady in time, okay, time independent. So we have actually two spatial variables. We have x and z. Pz is 0. By the way, I did not say this before, but the subscript means the partial derivative with respect to the respective variable. Okay, so Pz is 0, which means P is independent of z. So that's why P is a function of x only. And then let's integrate once this guy. By the way, P is independent of z, so this is like a constant with respect to z integration. Okay, so we integrated it twice, apply the boundary conditions, this one and this one. That's what we get for the velocity in the longitudinal direction. Okay, so U of z is given by this expression, and then actually, if we want to, we can find W after we found U, so we can substitute here and integrate it once for W and find W, but we don't need this for the purpose I have in mind. Instead, I want to write the flow rate in the x direction. Okay, so the flow rate is just a Q. It's just I have my velocity profile in the x direction as a function of z, so I integrate it across the layer between 0 and h, okay, up to the location of this upper surface. And if this is my flow rate in the x direction, but it's actually constant because of the fact that nothing is time dependent. So Q should be a constant, should not depend on x, okay? And okay, so I can substitute U because we have it here. So I find this expression for a Q. Okay, I have this expression, and then I differentiate with respect to x. So a Q is actually a constant, which I don't know so much how much is this. Why? Because I don't know the pressure. I have only the expression for the pressure here, but I don't know how much is this. Okay? But if I differentiate this equation with respect to x, so I will get rid of this Q. That's what I get. Okay? Now this equation is normally called Reynolds lubrication equation. And it's quite useful. But now let me ask you a question. Okay, what the hell we need from this equation? Okay, H is given. So the surface, the profile of this upper surface is given. Okay, so what can we find from this equation? We can find P. We want the pressure from this guy. Okay, so what's next? Okay, so we integrate this equation twice. We have two boundary conditions for the pressure, okay, over here. And then finally, we find a pressure. And this is the equation, the expression for a pressure profile in X. Okay, now please pay attention to the following. I don't impose any prescribed version of the upper surface. And whatever it is, and, as long as it satisfies the prerequisite, which is the gradients should be very small. Okay, so this is the expression. If I know what is H, I substitute it here, 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 everywhere. I know how to integrate. Okay, almost. Okay, and then I find the expression for P. Okay, so so now if I want to ask myself, what can I get from here? Well, I can, for a given H, okay, I can calculate this expression. Actually, I can make it dimensionless and to calculate and to draw a graph for this EP, which is EP minus PA divided by 6 mu U0. So this expression is shown here as a function of X, or X over L. Okay, for some prescribed function describing the location of the upper surface. This is probably just for a linear function. Okay, and okay, so what special we see here is the following. It starts from 0 because we impose the two boundary conditions here and here. Okay, it starts from 0, it goes into 0, but before going to 0, it has a maximum, and the maximum is sort of very distinct. Now, what is more important is the following. Okay, remember alpha, this is a maximal gradient, maximal value of the gradient of this surface. Okay, as alpha goes to 0, it turns out that the maximal pressure here, this value, goes as 1 over alpha. Okay, you can ask why that. Do I have a chalk or something? It's over here. This one. Okay, let's assume, okay, H is 1 minus alpha x. Okay, so this is H, so this is X. Let's assume it's something like this, and alpha is small. Okay, so for example, if I look at this guy, okay, so it will be integral between 0 and x of dx over h squared. So 0 to x dx over 1 minus alpha x squared. Okay, and then let me multiply this by alpha and divide by alpha. So I can do this very easily, this integration, but this guy, 1 over alpha, sticks out. Okay, so that's why we have it 1 over alpha. Now, if you say that the others will be different, no, you are wrong, because, okay, this will also give 1 over alpha, and this will give 1 over alpha squared. No, it will also be 1 over alpha. So basically, the whole thing goes as 1 over alpha, which means that if alpha is small, the maximal pressure will be large. Okay, and this will be very important for the rest of the story. Okay, now, if we assume that the location of this upper surface slowly varies with respect to time, then I can extend this Reynolds equation to the time-dependent version, and that's what I get. So basically, this is what you saw before, and now we have this additional term, which is a time derivative of the location of h with respect to time. Okay, so basically, this is the one-dimensional equation, and this will be intermittently used here in these talks. Actually, the one-dimensional equation, it's what's called 1 plus 1. One time and one spatial direction, x. Okay, so it describes a two-dimensional physics. So remember, if we had a two-dimensional slipper bearing. Now, if I want to extend into the three-dimensional physics, so then I will get a two-dimensional equation like this. So instead of all of these derivatives, with respect to x, now we have this a nabla operator, which will be dx dy, and the velocity which will appear here, it will be two-dimensional, of course, but the equation will be of a similar type one time, and now two-dimensional space. Okay, it will describe a three-dimensional physics. Okay, so now let me reiterate. Sorry, here. From this equation, this Reynolds equation, either in this form or this form, either one-dimensional or two-dimensional form, what do I know and what do I want to get? So the main thing I know, this is h. Okay, h is a function of x and time, and the only thing I want from this equation, I want to know what is the pressure distribution inside the channel. Okay, things will be similar later, but vice versa. I will. Okay, let me continue, and then we'll come back to this point. Okay, so now let's forget about all of this, and now let's look at films. Okay, keeping in mind that there is this creature of slipper bearing. Okay, now just to make complicated things simpler, let's consider a two-dimensional case. Okay, a two-dimensional case, a three-dimensional case, it can be treated in a similar way. It's a little bulkier, but doable. Okay, so the two-dimensional case, again, we have a two-dimensional mass conservation equation. We have two components for the Navier-Stokes equation. Again, incompressible Newtonian liquid. Okay, life is good. Okay, now nabla squared is a Laplacian which is given in xz plane, and we have in addition, we have this guy phi, which is a potential for the conservative body forces, showing here and here. Okay, now the boundary conditions. Well, let me show you maybe, no, sorry. Okay, let me reveal the whole truth. Okay. So it looks like this. Okay, here is a solid substrate, and on top of it, okay, so this is x direction, this is z direction, everything is two-dimensional. And on top of this guy, we have a liquid film with a possibly deformable interface, which separates between the liquid and the gas outside, or whatever is outside. Okay, and okay, a gas on this picture. Okay, now, the boundary conditions on the solid wall. Okay, at z equals 0, w is 0, so there is no penetration. Basically, if there is no slip, so u should be 0. Effectively, for beta equal to 0, we are back to no slip. Okay, but sometimes if people want to use the same machinery as I'm going to explain or to introduce, to study drop dynamics. And then it's very hard if the drop is finite and it sits on top of a solid surface, then it's very hard to explain to people or to convince people how come you have this u equals 0 requirement and the drop moves along the surface. Contracts or expands. Okay, so just to alleviate this a problem, people say, okay, let's introduce a fiction, and this fiction is called the slip coefficient. So for beta equals 0, we are back to no slip condition. For small beta, it's not far from no slip, but it's already. It allows you to move the contact line without a fear that someone will attack you and will say, no, you violate the first principles. Okay, how come as a drop moves? Anyway, I will not make use of this beta, so let's assume that beta is 0. And I didn't say anything about slip. Okay, fine. Now the most important and the most frustrating part, I would say, about the boundary conditions at the gas-liquid interface. Now the interface is given again with this h function. Now h function, which means the location of the gas-liquid interface, it may be time-dependent and space-dependent. Space-dependent means it may be deformed in a way you don't know a priori. You have to find the solution as a part of the whole solution. And it may move. It changes shape this way, that way, so that's why time is also one of the main players here. Okay, so now the goal is to derive a partial differential equation to describe, or to be able to describe, and mathematically describe, or physically, or both, okay, to describe the location of the interface at any time, at any spatial location. Okay? The problem is not very easy, and the whole thing is subjected to the action of some physical factors. I will talk about them later. Okay? But basically, I mean, the main thing we want to describe the dynamics of this liquid film. Okay, so let's see how it goes. Okay, now, what kind of boundary conditions we have? The first boundary condition is called kinematic boundary condition. I don't know whether you are familiar. Okay, I speak about students. You know. Okay, what is a kinematic boundary condition? So the kinematic boundary condition in simple terms, it tells the following. Now imagine this is the surface, the liquid surface which is shown here, this stuff. Okay, now think about the following thing. Think about a mathematical surface, just an abstract surface, okay, which moves in the space. In the three-dimensional space, it moves, it may be deformed while moving, it does all things, and we don't know about this too much. So I may look at this guy, at this location, from actually two different points of view. One is to say, or to ask, what is the normal velocity, or the velocity in the direction normal to this location at the surface, from the point of view of the mathematical surface which moves in the three-dimensional space. So let me call it Vn, normal velocity of the surface. Okay? But at the same time, I may ask another equation. What would be the velocity of the liquid particles, or liquid particle, which sits exactly in the same location, and it moves as a part of the fluid velocity field, which is imposed or exists in the liquid film. Okay? And let me, well, there is only white, but let's imagine that this white is not white anymore, it's red or whatever. Let's call Vn P, or okay, P, particle. Okay? So these two identities are in general different. But the kinematic boundary conditions, it tells you that these two things must be the same. So Vn P should be Vns. Okay? These two things, so the interface, in this case gas-liquid interface, is a material surface, which means that it moves exactly in the same way like liquid particles inside the liquid layer, sitting exactly at the same location, they move. This particle moves here, so the interface moves after it. This one wants to go there, so the liquid-gas interface at that location, it goes after it. Okay, they are not separate identities. They follow each other, but only in the normal direction. The liquid particles may slip along the surface. It's not disallowed, but it's disallowed to overpass or to cross the material surface. It's disallowed to the particle to do it. They don't cross it. The interface deforms after the particle. Okay, so this is actually the essence of the kinematic boundary condition, and it can be derived in this form. Okay, now what else? Now we have stresses, and we have to write a balance of stresses, and it's written here. I will not derive it, of course. You can read it here and there. and it's shown here. A T is the stress tensor in the liquid phase. Okay, and this is a normal vector, unit normal vector to the interface at any location along the interface. A tau, okay, T. T is a tangential vector, so it appears here. Okay, now H, this fancy H, is mean curvature of the surface of the interface, and it can be shown that it's given by this expression 1/2 of divergence of the normal vector n, or in the two-dimensional case, the simplest one, of course, it's given by this nice expression which you learn in the, I think it's the beginning of your mathematics studies in the university. Not in the kindergarten, but in the university. Okay, okay. So this tangential and the normal vector, it can be given by these expressions, and actually, yeah. Now sigma. There is this guy sigma, the surface tension of the interface. Well, I hope you are all familiar with that. And now surface tension, sigma, may change from time to time, may change as a function of the temperature or a concentration of a solute in a solvent, and it can change chemically, it can change electrically, I mean, under different kinds of forcing. So a possible variation of surface tension along the surface is given by this guy. So if a Marangoni effect is involved, so, or you heat your liquid and the temperature is non-uniform along the surface, so then surface tension varies, and this guy gives rise to the Marangoni effect. And this F is an external forcing with two components. Pi, this is a normal component of external forcing, and tau here, this is the tangential component of the external forcing. We'll come back to this a little later, but basically this is a general situation. Okay, so after showing you these boundary conditions and the equations, so you may still think, oh, the problem is simple. No, let me convince you it's not. No, it will take some time before I finally convince you, but let's have a look at these expressions. So the expressions, these are expressions written in a very shortened way, so it's very hard to appreciate how complicated they are. But even if you look at these guys here, so you immediately understand that the whole problem is nonlinear. And imagine that, okay, H is an unknown function, and you want to solve, at the same time, you want to solve the problem for the flow field, for the pressure field, with an unknown H, okay? And the equations and the boundary conditions are nonlinear, so we understand it's not easy. But now someone can say, oh, I will bring a very big, very fast, and very expensive computer. It will solve for me everything, whatever I will ask him. No, it's not that easy, because the problem itself must be solved in the domain you don't know where to solve, because the location of this H is a part of the problem. You first need to understand where to solve the problem and then to solve it, or maybe to solve it simultaneously. So it's not easy. And then we'll see that it's not easy at all. Some people make living out of this, but I will not mention names. Anyway, why it doesn't work? Okay, so now let's try to derive some systematic approach to reduce the complexity of the problem, and maybe to come up with something which is similar. I'm actually hinting at the outcome of the whole thing, to derive something which will be similar, at least optically. It will be similar to the Reynolds lubrication equation which I showed you before for a simple problem of a slipper bearing, which is really a simple problem. This is much less simple, even much more complicated, and we'll see it. Okay, so let me begin the story with scales. Okay, we are physicists, so we want to understand what the relevant scales are. Okay, so let me first assume, let me start with, let's assume that lambda, this is a typical or characteristic wavelength of the disturbance in the x direction, in this direction. Okay, and let's assume that the distortion of the interface are at long scale, which means that the length, the wavelength of the disturbance is much larger than some typical length scale in the z direction. Now, what is the typical length scale in the z direction? Well, it's say the average film thickness. Let's call it H0. Where is H0? Here. The mean thickness of the film. So you pour a liter of water or a liter of, I don't know, of some other liquid, alcohol, okay? And it may be deflected, but you know how much you poured and you know about the extension of the film, so you can figure out what would be the mean thickness of the film. So let's call it H0. Now, let me assume that the ratio between the two, it will be assigned by epsilon, and this will be much smaller than 1. So I think that once I say there is a parameter which is much smaller than 1, so I think many of the people think, okay, so there will be probably some asymptotic expansions, and you are right. Okay, so I need some small parameter, some typical small parameter for my asymptotic expansion, and this case, this epsilon, which is the ratio between these two values, is a good candidate. Or, for example, the ratio between the territory of Israel and the territory of Russia, it may be also a natural small parameter for any asymptotic expansion. Anyway. Let's come back here. Okay, so we find a typical or a good candidate to be a small parameter for asymptotic expansions. Okay, so now how about z? What kind of natural wavelength or length scale I can invent for z? Well, for z I don't need to work hard. I have this mean thickness of the film, so why not? Okay, so let me define this z as a capital Z. It will be non-dimensional value, so it will be z divided by h0. So I don't count the length in z direction, not in kilometers, not in nanometers, not in whatever, in units of h0. Fine. Okay. Now, if I want to define the dimensionless x value, so what we are saying is the following: if this is x and we have this deflected surface and the wavelength is lambda, okay, so basically the good choice for dimensionless x would be this. Okay, right? I would count, again, not in nanometers, not in kilometers, in units of lambda. But lambda is h0 divided by epsilon, by definition of epsilon, right? So that's why I get this. Okay, h0 divided by epsilon, it's exactly lambda. So it's scaled by lambda. It's not a trick, not mathematical a trick. It's just reality. Okay, that's how I scale this. Okay, so now I would assume that there are no rapid variations of the fields of interest, not the pressure field, not the velocity field. They don't vary very fast. So that's why we'll assume that all derivatives with respect to x and with respect to z will be of unity order, of order 1. Okay, now let's look at the scales for velocity. Okay, let's assume that there is a typical velocity, for example, u0. It doesn't really matter what is this. for the sake of discussion. Then when we come to real problems, so then we'll figure out what would be this U0. Let's assume that there is some U0, like in the slipper bearing problem, so there was a U0 which the whole system was forced by this movement of the plane, so it was U0. Okay? So let's define a dimensionless velocity as a ratio between U and U0. Now how about W? Okay. With W, it's not easy. Why? Because, well, it's natural, of course, to scale W also with U0. Yes and no. Why? Because if I'm back to this equation, which is mass conservation equation, let's write it here. Let's see what are the problems here. So we say that a capital U, it's U divided by U0, right? And now we have a capital X, we have, okay, what was the definition? Yeah, here. Okay, epsilon X divided by H0. Now I have to find an eraser. Ah, there is one. Oh, this one? Okay, it's wet enough. Okay, good. Ah, fine. Okay, now we have Z as Z divided by H0, right? Okay, so now let's look at this equation. It's Ux plus WZ equal to 0. Okay, so okay, by the way, dx, if I want to differentiate with respect to x, what do I find? I first differentiate with the capital X, and then I differentiate this guy with respect to small x, so I have epsilon H0. So which means that the derivatives with respect to x are small, because they have epsilon. Okay? It's something to remember, because I assume that everything is very gentle, very slow in x. Okay, so now what do I have here? Here I have U0 epsilon H0 U sub x. Now dz, by the way, dz is d capital Z with H0 somewhere here, right? No, it's 1 over H0, okay? So I go here. So it's 1 over H0. And now I have to understand what would be the good candidate for W, because if I say that a capital W is just W divided by U0, okay, so then I will get U0 here, and I will get dW dz, okay, equal to 0, okay? Now, don't forget epsilon is small. So if I send epsilon to 0, what happens? This goes to 0, so I can forget about this, but this sticks out. This remains, which means if this goes away and this remains, it means that Wz equal to 0. And if Wz is equal to 0, so this must be also 0, because I go back actually epsilon is not 0. It may be, however, small, but not 0, okay? So then there is a problem here. So that's why it's very important to understand that W, it cannot be scaled like this. It should bear some epsilon to balance this epsilon. So to have mass conservation, the claim is you cannot give up neither this one nor this one. Most of them must be there, because otherwise you lose your mass conservation. So the solution, you may find the solution, but the solution will be wrong. You must preserve this mass conservation Ux plus Wz equal to 0 no matter what. Okay? So that's why you need this epsilon, not this one, but this one. Which means, I think about this, which means if U is order 1, okay, W, I mean, I'm speaking about dimensional variables, not non-dimensional, dimensional variables. If this U is order 1, okay, like written here, I don't deny what I wrote, but then it means that this guy W must be of order epsilon, okay, to keep the balance between the two terms. Now, what it should remind you, I'm sure that everyone here in this audience learned at this stage of his career, or that stage, boundary layer theory. Okay, and remember, when you had this Blasius problem, okay, and the boundary layer is very thin, and this velocity was order 1, there was a little guy in this direction, which was responsible for many things, like the expansion of the boundary layer. As longer you go along the surface, this boundary layer expands in the z direction. Okay, this is exactly because of this, similar. Okay, so the main issue, W should be small, should be of order epsilon, and this is the right scale for the dimensionless W. Now, okay, how about time? This is the trickiest thing. Now, at time, well, if we have u0 as the characteristic velocity, and we have h0 as the characteristic thickness of the system, we may say, oh, it's very easy. The ratio between this guy and this guy, u0 divided by h0, that's exactly 1 over time in units, right? So that's why it would be absolutely easy to scale or to define dimensionless time as u0 divided by h0 times a physical time, okay, exactly like this, but without epsilon. It would be perfectly okay from the point of view of non-dimensionalization, but there are many other arguments which may hint you, no, it's not exactly this. Why? Let's go back for 1 nanosecond to this guy, to the kinematic boundary condition. Now, okay, if time is important here, so I cannot say, okay, this guy is important, but this one, well, I don't know what to do with it, let it go away. No, it's important to say. Why? Because if we want to satisfy this requirement, you must keep, okay, all of the three in this boundary condition together. Which means, let me again use this sophisticated device. Okay, and not yet. Okay, so let's go back there. U is this. W is somewhere, it's here. This is W. Okay, so let's substitute everything back. Let's see what happens. Okay, H, by the way, if I want to come up with the non-dimensional location of the interface, I think everyone will agree if I do this. Well, the typical length in the z direction is the mean thickness, so why not? Okay, fine. So let me see what happens over there. Now, okay, so UHZ, UHX. UHX will be the following. U is this, is U0 times little u, times a capital U. Okay, HX will give you H0 times H divided, differentiated with respect to the capital X, and times epsilon H0. That's what you get from this guy in the dimensionless form. Now, how about W? W is, well, that's easy. W is just epsilon. No, something is wrong. I think epsilon should be here. Right? Yes. Just to make sure that I'm not cheating on you. Yes. Over here. Okay. Okay. So which means that W should be actually epsilon U0 times capital W. Now, okay. How about HT? How about this guy? Okay. HT okay, I know what is h. ht is h0 times ht, capital T. And if I opt for this version, what do I have? I have u0 over h0. Okay, so now look at the three components of this boundary condition. This is one of them. This is the other one. And this is the third one. Okay, now I put all of them together. So now I'm cooking this soup. And what I find, and now I send epsilon to 0. What happens? This one goes away. This one goes away because epsilon is in. How about this one? It stays. What does this mean? It means, okay, one of the two. Okay, either I'm going to lose a part of this kinematic boundary condition, so which means if this is 0, so it means I can forget about this, and then I solve or use the kinematic boundary condition with no time dependence, and then I lose something. And I already forgot what was as a second one, but as a second one is also wrong. Okay, so what is the main conclusion? The conclusion is that I must include something here which will have the same epsilon like here. And then I will cancel epsilon, and all the three ingredients will be still there. Okay, so what does this mean? It means that, the time variation should be slow. And it means that it should be epsilon here. So the time derivative will be also of order epsilon. Okay, so this is the time scaling. Now, how about the pressure? Okay, we talked about independent variables. We talked about velocity. How about pressure? Okay, remember in this lousy slipper bearing example, okay, one of the main conclusions was if alpha goes to 0, so the maximal pressure goes as 1 over alpha. Sorry. Now alpha is epsilon. Okay, for the sake of our discussion. That's why the pressure, okay, this is the dimensionless pressure. This is the pressure, the physical one. There should be some epsilon just to cancel this 1 over alpha in that example here. Okay, so the pressure must be large. As in the scale of 1 over epsilon, so which means, sorry, if the pressure is 1 over epsilon, so the normalized pressure will be order 1. Okay, so and the rest, I'm not going to comment on that. Okay, if the rest follow these arguments. Okay, so this is the thing. Now, okay, after we introduce all of these scales, now let's look at the equations and the boundary conditions. Now you will understand that things are not trivial. Okay, so these are the Navier-Stokes equations and the continuity equation while rewritten in dimensionless form, in the scaled form. Okay, now see, look here. The continuity equation now is written in dimensionless form. It doesn't have any epsilon. Where is epsilon? Epsilon went away because it was already cancelled. In every term had epsilon in it. It went away. It doesn't appear anymore. Okay, so this is the x component of the Navier-Stokes equation. This is the z component of the Navier-Stokes equation. We'll come back to this later, a little bit later. Now the boundary conditions at z equals 0, the floor, w is 0. I forget about beta 0. Beta is slip coefficient. You didn't see it here. U is 0. You are back to no slip condition. Now how about the boundary conditions at the interface? And now we see all of them. This is the continuity, the kinematic boundary condition with all the three components in, nothing is missing, and these are it's exactly these, but now it's written in the normal component and a tangential component with respect to the interface, so you can appreciate how complicated they are. Okay, so now imagine you need to treat or to satisfy these boundary conditions when you found and bought the most expensive, the fastest computer in the world, and you want to solve your problems. And now you see that you face a problem much more serious, much more complicated than to find and to buy that big computer. Okay, so the complications are visible. Another question is how to overcome the complications and to find something which you can rely on. Okay. So, so this is a continuation of the previous slide. What you see here, okay, again, the boundary conditions, but now let me explain what are the new players in the field here we see. Well, first, sigma, this sigma is a dimensionless surface tension scaled with some typical value for sigma, which is sigma 0 here. Okay, H is the dimensionless location of the interface. And now we have two dimensionless parameters. One of them is C. Let me start with this one, is a capillary number. I think in American it said a capillary number, but in British it's a capillary number, so we will not argue about which version is correct. I think the Israeli one is definitely correct. Anyway, the capillary number, and the capillary number, this is a ratio between the capillary effect and the dynamic effect, which come into play through this mu u0 term. Okay, so the stronger is the surface tension, the smaller is the capillary number, but in the equation, in the boundary condition, we have the inverse capillary number, C minus 1, which goes in the same direction. Sigma is larger, C minus 1 is larger. Okay, and we have Reynolds number here, which is a typical expression for it. Now you don't see it because it's hidden in the previous slide. It's over here. So the Reynolds number appears in both components of the Navier-Stokes equations. It's here, and by the way, we see this is the only reminiscent of nonlinearities. Well, the only reminiscent. The only terms in nonlinear terms in the Navier-Stokes equations, which are just advective terms. Okay, so we'll see what to do with them next. Okay, so now before we continue, let me try to combine this guy, the kinematic boundary condition, with the continuity equation. Why? Because sometimes it's very convenient. So what I do is the following. Let me take this guy, which is a continuity equation, and this is the kinematic boundary condition. All of them are in dimensionless form. Let's integrate across the film, across in z direction, between the substrate and the location of the interface, which is z equal h. Okay, so let's do it together. So we integrate in the z direction. So integral of 0 is still 0. Okay, integral of the first guy, integral between 0 and h of ux of this one dz, plus integral of this one. But this one is very easy to integrate because it is integrated in z direction and it's wz. It's just a pleasure to deal with. Okay, so out of this guy we have these two, right? But well, if it works, works. Okay, but this one is 0 because of the boundary condition. Okay, so life is even happier than ever. Okay, so this one, okay, is killed. Okay, so what's left is minus w at z equal h. This one is just integral of this one because the sum is 0. Okay, and now you substitute this into this kinematic boundary condition. Remember, the kinematic boundary condition holds at the interface only. It's not everywhere. It's just at the surface at z equal h. Okay, so at z equal h we have 0. This is the same 0 like here. Okay, h sub t plus this u at z equal h times hx minus w, but w it's not w at z equal h, but minus w at z equal h and this integral. Okay, so we replace it here, and a miracle, Okay, so we have here a full derivative with respect to x of this integral between 0 and h of u dz. But now I'm sure, okay, I bet 100 rubles that everyone now understands that now there is a relation to the q. Remember in the slipper bearing case we had a q, a flux, mass flux in the x direction, so that's exactly the flux rate. Okay, fine, in the x direction. So this is normally called kinematic boundary condition. It's the same way, but I prefer to call it consolidated kinematic boundary condition because it has a connotation of something combined. So this is a combination of the mass conservation and the kinematic boundary condition. Okay, so now back to our perils. Okay, so now I want to look for a solution of this terrifying problems we saw. Okay, before I want to solve it using a method of asymptotic expansions. So I expand everything what I see, what I don't see, the pressure field and the velocity field into series of epsilon. Epsilon, remember, is a small parameter, no matter how you define it. Okay, okay, and sort the terms. Okay, order by order. Okay, so what I say, okay, let me look only in the beginning at the components of the whole thing which do not have epsilon in it. So I send epsilon to 0, and what is left is that what I'm dealing with. Okay, so let me assume the following. Let me assume that the Reynolds number is at most order 1. Why? If it's at most order 1 or smaller, as epsilon goes to 0, so then these guys, the convective terms in the Navier-Stokes equations, this and this, they are much smaller than 1. So at leading order, I can discard them. I can forget about this. And by the way, what is my gain? My gain is that my equation, at least, become linear. Why they became linear? Because I forgot, or I made everything possible to linearize, so to speak, the equations. Okay. Now, but nonlinearity, yeah. Okay, so the nonlinearity in the equations disappears. But my goal is not to linearize, because to linearize is not a big deal. Just forget about nonlinearities and say, okay, eureka. No, I want to find still a nonlinear description for the problem, keeping a leading order terms only. So somewhere I will recover at least some nonlinearities for my description, and it's not wonder that they will be recovered through this consolidated kinematic boundary conditions which we just discussed. Okay. Okay, let's see what happens with the boundary conditions. So this is the normal component of the boundary conditions of the dynamic boundary condition at the interface. You see it by a pressure, a presence here. So what do we have here? We have a pressure. We have this imposed normal a component of the forcing, of the external forcing. We have some dynamic addition to the normal stress, which comes through viscosity. So, okay, so previously mu was multiplying these guys. And we have a capillary effect here due to surface tension. Okay. Now, if I say this guy is very small, why? Because it's epsilon to the third. So if I say this guy goes away, so then I will find something, but this is something will not be viable, will not survive the life exam. Okay, it will not stand by any standards. I will tell you why later. But we understand now if we forget about this guy, we'll lose any of the effects which are related to capillarity. Okay, and we don't want it because we really okay, have a free surface, and if we lose or if we forget about capillarity, the world will not be the same the next day. Okay, you have to keep it by force, which means that somehow you have to, if you want to keep only the leading order terms, you have to assume at least that C to minus 1, so the inverse capillary number is very large, is order of 1 over epsilon cubed. Okay? And this is not something imaginary, because if you think about even water, okay, if you calculate inverse capillary number for a water film at any temperature, at room temperature, for example, doesn't matter whether it's 19 or 21 degrees Celsius. If you take a film of about 1 millimeter thick, okay, H0 is about 1 millimeter, assume that the inverse capillary number will be thousands. It will be 5,000 to 15,000 depending on the temperature, depending on the thickness, depending on the, okay? So which means that assuming that inverse capillary number is large is not something like you assume, let's assume a spherical cow. No, it's not. It's a real thing. Of course, you cannot assume that the inverse capillary number is very large for a film of very low viscosity. It's different. But for normal liquids with not that thick, a small thickness, it's really a plausible opportunity that and possibility that the inverse capillary number is very large. Okay, so we'll assume that the inverse capillary number is very large. So we'll introduce it C bar, and C bar will be order 1 because by its definition it's C multiplied by epsilon to minus 3. Okay, so this C is order 1. So that's how we save the capillarity effect here. Okay, and this is, okay, I wrote that this is very essential to retain surface tension effects, and we'll see later why, because it's really crucial, because if you lose it, so you lose the whole approach. Okay, now let's go back. Let's go back to the equation and the boundary conditions. Let's look only at leading order terms in epsilon. Okay, this is what is left after the Navier-Stokes equation in the x direction. And if you don't have this guy, phi, if phi is 0, or if you incorporate it into p and define in UP is the old p plus phi, that's exactly, I believe, well, I hope. No, it's not written here. Maybe it's the next slide. It's exactly what we had for this slipper bearing problem several hours ago, right? What time is it? It's just the beginning. Okay, so should we make a break or what?
Maybe it's not needed right now.
No.
Usually without break.
Without break. Okay, so I have a few more hours, right, today. Okay, fine. Okay, so so that's what we have for this equation. Okay, for Navier-Stokes equation in the x direction. Now, how about z direction? Look at this. Pz, if phi is 0, pz is equal 0, or if you incorporate phi into p, nu p is old p plus phi. So nu pz equal to 0. That's exactly what we had for the slipper bearing. Remember, a pressure was independent of z direction. So it looks like we are going back to the same equation, but not precisely, almost, but not exactly. Okay? So now, at z equals 0, I forget about beta 0, u equals 0. At z equal h, that's what we have. Now, if this guy, tau, okay, so okay. Now, by the way, to make a progress, we don't need to find W. We don't need to find W because this is our new form or consolidated kinematic boundary condition. It doesn't have W because, okay, so you solve this equation for P, you integrate it for U, you find U, you plug it in, you don't need W. Unless you are very curious what happens with W, then you can come back to the continuity equation and integrate it. Once you know U, you integrate, you find W. But it's not needed. It's an extra effort. And nowadays, not too many people do it, because you can apply this consolidated form of the kinematic boundary condition. Now, one more thing. It's here. I remember it was somewhere. Okay? These were the equations we derived for this one-dimensional slipper bearing. Now you compare between this and this, and this and this, and this and this. Okay, what was supposed to be there, you don't see the difference. So which means that these two problems, at least at leading order, they are almost the same. Or maybe the same, but not the same. Okay, we'll see. Okay, so now the solution. Okay, so we want to solve the problem. We find the weakest guy here in the country or in the town, and we solve it first. Okay, so a p plus phi definitely is z independent. Okay, fine. So we define nu p, this guy, and then a p is independent of z. But on the other hand, we have a boundary condition for a p at z equal h. So if p is independent of z, so this is a value, right? Okay, so it goes like this. So we find a p with this capillary component. Then we integrate. We go back here. We solve it for u. If you look at this guy, and if you take tau 0 to 0 and this e to 0, so this one doesn't exist, beta 0 is 0 because we don't want to discuss it. So we are back actually to the same expression as we got in the beginning, except for u0. There is no u0, u capital u0, u equal u0, right? So the drag velocity in the lower surface, it's not existing here. So that's why we get this expression. We substitute it into the consolidated boundary, kinematic boundary condition. We find this equation. We find this equation now, and it describes a two-dimensional physics. If it's not enough for us, if it's not complicated enough, so we can complicate it more, now we consider a three-dimensional physics. So then this becomes this. It looks almost the same, but instead of these derivatives, now we have all kinds of gradients, not really a pleasant thing, but if we have to, we have to. Okay, so that's okay. This is the normal gradient. So basically, okay, what we derived now, it's usually called an evolution equation. Evolution equation for okay h. Now let me explain you what we get here. Okay, so this is the Reynolds equation as we derived it about an hour or more ago, right? And it was very simple. From this equation, given h, given the location of this upper surface, what we wanted to find? We wanted to find the pressure. We wanted to find the pressure. Okay, remember this, a curve with a peak. If alpha goes to 0, this guy goes as 1 over alpha and everything. The evolution equation for a film is this one. Okay, now let's assume that beta is 0. We don't want it here. It doesn't complicate much, but okay, let's discard it for the time being. So what we have here? Okay, here we have some partial differential equation for h. Now, don't forget, you see here this guy. You see this. But this one is already found in this form. So if I have h, okay, assume for a moment. If I have h, so I can calculate this guy because this is given and this is given. Okay, so basically here I have, yeah, something like here. Okay, so I have a second derivative of h from here, and there is one more derivative here, and I have all other components here. So the point is the following. Now I derived a partial differential equation for h. Okay, h is an unknown function. It depends on time and space, on t and x. And so this is the equation. Now this partial differential equation is first order in in time. And at least for this example, it's a fourth order in space, 4. Why 4? Because, okay, we have one derivative here, we have one here, and we have a second derivative here. So we have a nonlinear partial differential equation of fourth order in space, okay, and nonlinear. But let me at least attempt to convince you that this is a simplification. Okay, remember, in the beginning, we had a terrifying set of boundary conditions of equations, and we said, okay, how to solve it? The problem is nonlinear. I don't know how to solve it. Let me ask my father to buy me the biggest and the fastest computer ever in the world. So he goes to the supermarket, brings the computer. Now you have to solve the problem. How to solve it? I have to solve it numerically. In which domain? I don't know, because it's bounded by something. I don't know what is this. Okay? So the location of this guy, it's already a part of the solution, and I have no slightest idea. Definitely the computer doesn't have any slightest idea how to solve it. Okay, so here is the way how to solve it. Now, the price to be paid, well, everything in this life costs money, okay? If you want to solve a complicated problem, you have to pay, okay? Now you pay by what? You reduced your original set of equations and boundary conditions. You reduced it to this partial differential equation. The price is the high order of this equation in space. It's fourth order. Not too many people solve it every morning on the breakfast, okay? But okay, what is the benefit? The benefit is the following. If you solve this equation, okay, this is in dimensionless form, this is in a dimensional form, no matter which one you solve. You solve this equation, you go back. So you find h as a function of time and space. You go back, you find the pressure field, because you know h. Okay, you know what is this, you know what is this now, this is given, you know the pressure field. Once you know the pressure field, you go back here, and you find the velocity field, at least the x component. Why? Because you know what is p, you know what is h at every time, at any space, any location, so you can calculate this guy. You know the leading order component of the velocity field in the x direction. Okay, how about w? Well, we said it's not interesting. No, it is interesting, and then you go back here. Not here, over here, not here. Over here. You know what is u, you integrate this equation, you find w. So you know everything about the velocity field. You know everything about the pressure field. You know at leading order of epsilon. You know the location of the surface. So now if you know this location, I bring that a computer, now at least you know where to look for your solution. Okay, if you want to. Okay, so basically this is the greatest reduction. Now the question is what we can learn and how can we learn. Maybe it's a matter of $1 million how to solve this equation, or what can we learn from this equation. So we'll see it later. I hope it today, and if not it today, tomorrow. Okay, so basically this is the equation. So now I have to cope with this equation. It's not easy, but okay. So basically I want to know a few things. One thing, I want to know what it tells me, what kind of effects this equation wants to expose in front of me. I want to know a few more things, whatever I can get from this partial differential equation. In some cases, these equations are a little bit frightening when you look at it, but at the second glance, they are not so frightening. Okay? So we'll look at this later. So now the question is, when do we need to finish? At 5? At 5? Okay. What?
10 minutes.
10 minutes. Okay. So can we make it 15? Joking. Okay. So let's start and then we'll see how it goes. Okay, let's take the simplest case if possible. Let's assume, okay, so now it's a few examples. Some of them are good, some of them are better. Anyway, let's start with the following example. No sleep, beta 0 is 0, well, it was 0 anyway. A pi is 0 and a pi is a prescribed normal component of the external forcing. Let's assume none, 0. Okay, let's assume there are no body forces or gravity. Let's assume there is no gravity. So there are no body forces. Phi is 0. Let's assume that tau, this is a tangential component of external forcing, which is a prescribed shear stress at the interface. Now let's assume it's given and it's a constant. So the shear stress is somehow similar to a wind. You have a wind blowing along the surface, and it's sort of described by this external forcing. Let's assume that surface tension is 0. Is okay, a constant, a non-zero, of course. A 0 is bad. We'll come back to this later. A non-zero and a constant. It's not changing. It's not varying along the surface. Okay, going back here. Okay, remember beta 0 is 0, pi is 0, phi is 0, sigma is a constant, a tau is a constant. Okay, so what do we have here? Okay, tau 0 is exactly tau. That's a wind. Sigma is not varying with x, is 0. Beta is 0. This one doesn't exist. This one doesn't exist. P, if we look here, phi is 0, pi is 0, so these two guys are not there. Okay, so from this equation, I get this. I get this equation. Now, if you look at this now, and it's dimensional, it's not non-dimensional. It's written in a dimensional form. Okay, so when you look at this equation, well, it's more human, right? It's not frightening like the general one. Okay, so what do we see here? Here we see the first order derivative with respect to time. We have an advective term h times hx with some constant, and we have this guy which is a fourth order in space, as we said. Okay, so and sigma is a constant, so sigma is just a parameter, a coefficient. Okay, so it looks like it's not exactly, but it looks like it's, if we forget about this guy, let's forget for a moment. Let's assume that tau is 0. Okay, so it looks like a nonlinear heat equation. But it's not heat equation because it's not second order in space. It's a fourth order in space, but at least it looks like. Okay, now if sigma is 0, by the way, if it's 0 here, it's not a catastrophic effect, it's semi-catastrophic effect. Let me explain why. If sigma is 0, so we have actually a nonlinear wave equation. Okay, ht plus some coefficient tau divided by mu, hx equal to 0. This is nonlinear wave equation. So if you start with this guy at t equal 0, next moment what happens? Because of nonlinearity in the advective term, so wherever h is larger, so it goes fast, it goes a longer way. So which means this pulse which you started with, at the next time it will be skewed. And if it goes in this direction, so this leading front will be sharper. Okay, so it will become something like this, and then it will become something like this, going in this direction. Okay, what happens next is something like this. If you go to a beach and you look at the waves, so you see a wave breaking. That's what happens. So, and then you lose control. You cannot solve your equation because your h is a function. And once it gets to the catastrophe of the gradient, so it loses its functional shape. and you cannot continue anymore. So if you want to go beyond the breaking, you need to do something else. You need to describe it in some parametric way, not in a functional way. I'm not going to be involved in this kind of a discussion. So that's why I said it's a semi-catastrophic effect if there is no sigma and not a catastrophic. So it lives for some time, but not long life. At some stage, it overturns, and that's finita la commedia for this guy. Okay, anyway, going back to this equation. Okay, that's exactly what I said. Okay. Well, okay, I forgot already that I wrote that. Anyway, now, if you look at this equation, okay, now we are thinking, okay, what can we learn from this equation? Before we go we run to the computer our father bought for us, okay, to solve it. Okay, anyway, if I look at this equation and think, let's assume that h equals a constant and substitute it there, well, eureka, we found the solution. A trivial, though, but a solution. Okay, any h equal h0, which is a constant, satisfies this equation, right? You substitute 0 plus 0 plus 0 equal to 0. Big discovery, but that's it. So which means if I have this liquid film, and this is a surface, so it can stay indefinitely like this. It looks like, because it satisfies the equation. So now the question is, okay, what else? I mean, I cannot leave long this guy, and the way to answer or to respond to this query is the following. Let's assume that we superimpose a disturbance on this solution. And let's ask us what happens, how this disturbance evolves in time and space once superimposed on this flat solution. And this will give us an idea what happens if someone at the distance of, I don't know, 5,000 kilometers threw stone in the lake, in the local lake, and there was some sound wave emanating from that lake. It came here to our film and made a disturbance on the interface. Okay, what happens to this interface? Okay, so that's why we say, okay, let's assume that our h is not h0, but h0 plus some disturbance. The disturbance is h prime. And let's assume that the disturbance is very small. So the amplitude of this h prime is h0 prime, and this is much smaller than 1, or much smaller than h0, actually. Let's assume it's periodic in space. And if we have a periodic function, so we can expand it into a Fourier series. So this will be one component of this Fourier series with a wave number k, which is 2 pi divided by the length of the periodicity. And this is exponential form with respect to time, and this S, which shows here, this is a complex growth rate of a disturbance. Now let's look at the following. If this is a disturbance, so now let's speculate what different values for this S can make for us, and let's assume that the real part of this S is actually maybe in general a complex value. Okay, if the real part of this guy S is positive, so what does this mean? It means that because of this positive real part, this exponential term, at least its real part, will grow in time. Okay, this means if the real part of this S will be positive, it means that our interface will not remain flat. It will deviate from this flat state, which means it will become unstable. Now, what happens if the real part of this growth rate is negative? Oh, okay, we like it. Why? Because if this is negative, so the real part of this exponential function will decay in time. So which means it will come back a long time, In large time, it will come back to the initially flat state. Okay, so let's substitute this, okay, into this equation, and let's see what happens. And let's linearize, because we say that h0 prime is very small with respect to h0, so let's keep only linear term with respect to h0 prime, and discard the rest. Okay, so what do we find? We find this relation. So once we substitute it into the equation, we find this. And it tells us that mu is the viscosity of the liquid times the complex growth rate, okay, equals to what is written here. A k prime, it's the dimensionless wave number of the disturbance, it's just k multiplied by h0. That's what we get. Okay, so what can we see from here? Oh, many things. Why? Because, okay, we look first at the real part of this S. And what is the real part of this S? It's given here. Okay, how about its sign? Nobody knows what its sign. Negative. Sigma is E positive. A K to the fourth is certainly E positive. Sigma is E positive. H0, well, you cannot find a liquid film with a negative thickness. Okay, so the whole thing is negative. So it means, okay, it's written here. It means if we plot a graph of the growth rate with respect to the wave number of the disturbance, that's what you find. It's 0 only at k equals 0 and negative elsewhere. Okay, so what does this mean? It means that if you have a disturbance, it will decay. So it means that, well, I should say in the long wave, okay, range. Okay, okay, it will decay. So long waves will decay. So it means that if you have long wave disturbances, this interface will like to remain flat long time. Okay, but how about the rest? Okay, so if we look at this guy, so this guy corresponds to the imaginary part of the growth rate. Okay, so now imagine if we write, okay, S is SR plus I SI. This is the real part of S, and this is the imaginary part. So exponential of ST is something like this, multiplied by I SI T. But here we have also IKX, right? So we have here IKX. So this guy may be combined with this, like this, right? And if we look at this one, so what do we see here? We see a propagating wave. And the speed will be related to the ratio between SI and the K. Is that what we see here? So the imaginary part of this guy, that's exactly this. It's a phase speed of the wave. So if you have a wind, it follows from this equation or from this analysis, so the wave will decay, but before it decays, it will propagate with this speed, which is related to what? Which is related to tau, and it's related to the viscosity of the liquid. Now, how about a surface tension? Does it affect the speed of the waves? No, it affects only the rate of decay. So we see now, from this simple analysis, we can split the different effects. And we say, okay, surface tension is responsible only for decay, in this case, and not for the speed of the waves. Now the question whether the viscosity of the liquid affects the rate of decay, the answer is no. The rate of a decay is given solely by sigma and H0 and not by mu. So you see, even based on this equation which we derived, the equation itself doesn't look so nicely. It's a nice equation, but not the one which we'd like to solve every day, 5 times a day. Okay? But at least it's definitely much simpler than the original problem. Think about, you have to draw these kind of conclusions looking at the original equations and the original boundary conditions, which were really terrifying, okay, by their own, how they look like. So this is the point. Now, just maybe to conclude for today, I must say that not the entire world is not solely long wave. There are some short waves. Well, there are big guys, small guys. So there are long wave disturbances, and there are some short wave disturbances which are much shorter than the long one. And it turns out that this view on the world, imagine you climb on the wall of a fortress, and in the wall there are windows, very narrow windows, so you can see through them what's going outside, and if you have an enemy coming by, so you can shoot through this very narrow window. Okay, so it looks like if you want to concentrate on long wave analysis and you look or you stare at the world through this narrow window, it doesn't mean that the whole world looks exactly like this. No. You look at the world through this narrow window, you get a piece of information. It doesn't mean that the whole world must now obey your expectations, which you got through this narrow window. And in fact, if you give up this long wave analysis and do your analysis on the full equations, Navier-Stokes equations and all of these terrifying boundary conditions, but without assuming that the ratio between the wavelength, the mean thickness and the wavelengths is small, so you find that even in this case, some finite wavelength disturbances survive. Okay, so they can grow and not decay like this long wave analysis suggests. So the take-home message is not the whole world is long wave. Long wave analysis is very important because it gives you very nice results in many cases, but it doesn't mean that the rest is not important. Sometimes the rest is even more important than here, but at least we have to understand this. Okay, so I think it's the end of the story for today. So you will have a few more occasions in the next days. Okay, thank you.